Let's begin. You've got a homework that's due on Sunday, and today we're going to go over some more water problems that will get you ready for that. Specifically, it's related to Henry's law and gas transfer between the liquid and gas phase. Well, I don't grade the assignments. I have a homework grader, and so I wanted to make an announcement about the homework that it seemed like a few people may have been working with another student on like the computer part, and it's fine if you want to collaborate. You know, we spent a fair amount of time on the first day of class talking about what's acceptable collaboration, and so it's okay to check answers with another student, and it's okay to talk about the problem with them, but it's not okay for you both to be sitting at one computer and then only do one thing and print it out 2 times. That's not okay. So there were a few students that applied to on this assignment, and you probably noticed that there were marks taken off for that. You can redo this problem, just one time leniency. You can redo the problem by yourself. But if it occurs in the future, then that's going to be a case of inappropriate collaboration that would need to be brought to the dean. I expect you to do the homework yourself. Now, as for the other question that there's too many marks being taken off, you know, if you think that there's something that's been graded wrong, you know, like if the grader took off points and you did it right in the first place, then please let me know, because I want to make sure that you get all the points that you deserve on the homework. Are there any other questions or comments about the homework? Yeah. Are you going to drop off any homeworks? No, I'm not going to drop any homework assignments for the semester when it comes to the grades. Yeah. Other questions? All right, so the one that's due on Sunday, just to emphasize again, you know, it's okay to work with your classmates for checking answers and discussing the assignment, but the thing that you turn in should be your work. It shouldn't be a group assignment that everyone puts their name on and everyone gets points for. That's not how it works. So, you know, if you need to redo a problem from the assignment that I've just handed back to you, please get that to me by Sunday, and you can get the full credit just this one time. Maybe you didn't understand what the standards were, but that's how we're going to do it this semester. And so then after Sunday, when homework 4 is due, then there will be our second quiz of the semester. So what can you expect from the quiz? It'll be a lot like the first quiz, where I feel like the in-class exercise leads you to the homework and the homework leads you to the quiz. It won't be a surprise. It'll be something very natural and progressive, building on what we've already done before. And then the next homework, number 5, will be due on Sunday the 11th. So the semester is definitely starting to pick up. And I know that you guys have class on Saturday too, right? Because of the holiday being rescheduled. So we're all going to be busy. Today we're talking about gas transfer, and actually, does everyone have a copy of the notes? Everyone's got the notes? Unfortunately, it doesn't seem like the file copied onto my network drive for today's notes, and so what you've got is a little bit different from what I'll be projecting onto the screen, but I think we can make it work anyway, because the most important thing we're going to do today is the in-class exercise, and everybody's got that as well? In-class exercise? All right. So we're going to begin by getting to the reaction kinetics that we didn't have time for before. You've got a question? Okay, I printed 25, and there aren't any more on the table. So does anybody have an extra copy of the in-class exercise? One more of these floating around somewhere? I'll print an extra copy for you after class. I think somebody may have grabbed an extra one and doesn't realize it. All right. Let me just double check. I don't have it here. Yeah. I think probably somebody grabbed an extra. This is where we left off last time. And reaction kinetics for chemical reactions are the same for biological reactions. Do you guys have a question? Okay. Uh-huh.
I have a question.
Well, if you've got a specific question that shouldn't delay the whole class, we can talk about that afterwards, if it's like an individual question that's just for your paper. Yeah. All right. So chemical reaction kinetics are the same as biological reactions in that they can be zero order, first order, or second order. And one tricky thing that I want to give you some extra practice for is that we sometimes use the same equation for a consumption and a production reaction. And then the way that we handle it is with the sign of the K. Different books do it differently. I've used a different environmental book before where they would just show two equations and have negative KT in the exponent. But I think it's just easier for us to realize that for a zero order and a first order, if you have a consumption reaction, then the K will be negative. And that's what we see on the first in-class exercise problem is that, actually the second one. The first one's production. So I'd like you to work on this with a classmate, collaborate on this, and for now solve problem 1 and 2, because these are both zero order reactions, but the difference between them is that one has a negative K value and one has a positive K value. On the calculations, let's see here. All right, these are both zero order reactions, and I had somebody notice that the rate constant, the K, the units there are different than some of the problems you've seen in the past, where the units on some of the past problems were maybe like seconds to the -1 or minutes to the -1. So why is it that here the K value has a strange units of milligrams per liter dot seconds? So in the numerator is milligrams and the denominator is liters and seconds. All right, you have to look at how is this rate constant going to be used. Okay, here's the equation for it. We're going to multiply it by time, and to be able to add it to the original concentration, it has to be dimensionally homogeneous. It has to have the same units. And so we want it to have milligrams per liter after we've multiplied. So milligrams per liter, and then the seconds is also in the denominator. If we multiply by seconds, then we'll get milligrams per liter. And that's also what gave us the hint. I noticed a lot of you already realized you should multiply 10 minutes by 60 seconds. And probably you knew to do that because you saw here that it had seconds in the units. Now that experience is a really good illustration of why it's always a great idea to write the units as you're doing your calculations, is because if you're making a mistake, and it's so much easier to catch your mistake if you have the units listed there. Like if you only write the numbers, sometimes you won't see the error. But if you were doing this part and you had the units for the rate constant and then you had 10 minutes, when you start crossing things off, then that's when you'll catch the mistake, if you take the time to write the units. Okay, so it ends up that there's 7587 milligrams per liter is the concentration after 10 minutes. Okay? And then we did basically the same thing in problem 2, except for this is a consumption reaction. And so the K value is negative, which means the concentration is going down over time. Again, we have a hint of the units needed for time by the units of the K value, so converting 1 week to 7 days. I had kind of a funny experience in my cost analysis class. How many weeks are in a year? 52. And we were doing a problem in that class, and they did 4 weeks, 12 months, so 48 weeks per year. A lot of people did that. What's that? No, there's 52 weeks per year. Yeah. But I mean, there's not always 4 weeks in a month is the point. Sometimes there's 4.5 weeks in a month. So it's one of those brain teasers where if you just naturally do it too quick without thinking, then anyways. All right, so you convert into days, and then we are multiplying the time by the K value, and you get 83.5 grams per cubic meter. So any questions on the first two, consumption reaction and production reaction? All right. Now number 3, we're dealing with base E and logarithm. So go ahead and give that a try. I'm going to circulate around to see how it's going, and then we'll talk about the solution. Units is going to trip us up if we're not always careful about it. So let's take a look at problem 3. First of all, you don't know the initial concentration. And so it seems like everyone was on the right page of calculating the initial concentration by the given mass, 100 milligrams, and then the given volume, 5 liters. So we've got our initial concentration, 20 milligrams per liter. And then the time is 18 hours. And we don't yet know the K value or the units. But since we're given hours for the initial time, our units, probably it makes the most sense to leave it in terms of the time base being hours. Now here's the equation for a first order reaction. So we're going to use that to solve for the K. And you can see that what I've done is I've started with C equals C naught e to the KT. And then rearranging that to try and isolate the K value. So rearranging, this is what we get. You take the logarithm of the ratio divided by the time. So why is it inverse hours? Who'd like to explain why should the units be inverse hours? Hours to the minus 1. Yeah. Okay, because it's first order. Good. What's another way of looking at it? That's right. We can't put anything into E that has units up here. So the product of K and T needs to be unitless. So since T is hours, K should be inverse hours. And then multiply those two together and it's a unitless number, which is what we need. Very good. So any questions on this third one? All right. So now this is where the slides are a little bit different from what I've got here in the notes, unfortunately. This is a figure that comes from your text, and it's about when gas is, when a chemical is moving from the gas phase to the liquid phase. Okay, first of all, this word phase. Phase just means the 3 typical states of matter, which is solid, liquid, and gas. There's actually one more phase. Anybody know what the 4th phase is? Plasma. Plasma, right. But it's kind of rare. We can make plasma in the lab, but naturally occurring, usually solid, liquid, and gas. So let's imagine a container that has a liquid and a gas above it. We're going to be using this as an example a lot today. And in fact, we're going to watch a little video that kind of illustrates this. These figures that come from the book is talking about when you first start adding a gas into a liquid. So let's say that we had an open container, and so there's a little bit of gas above it, and that gas is dissolved in the liquid. Close the container and start pumping in CO2. What is CO2 used for a lot in closed containers and liquids? Do you know anything about carbon dioxide and bottled liquids? Okay. It can be used for heat exchange. What about beverages? What is CO2 used for in the beverage industry? Soda, carbonation, right. So during the carbonation process, if you start pumping in CO2, then it will get into the liquid. What this figure is showing is that when the concentration in the gas, on the x-axis here is concentration, when the concentration of the gas is higher, it has to travel across a film. And there's a gas film and a liquid film. And what that means is if we zoom in really closely here, let's take a microscope at the liquid and the gas. Okay, here's that same view. Here's the liquid, and here's the gas. Above the liquid, there's like this thin layer where it's starting to transfer through. These films that the gas is transferring when it's high or when it's low, there's a linear distribution in the concentration. And so on the left is when the concentration is going up in the liquid, and on the right, it's when the concentration is high in the liquid, but now it's going to be going down to match the concentration in the gas. Okay, just really quickly, let's watch a video that I found that kind of illustrates the principles of gas transfer. I had the link in my other notes, but I think we can find it again easily. Yeah, I think this is it.
The soft drink was born of the drugstore soda fountain, where pharmacists would serve up.
The headspace is what's known as, the headspace is the gas above the liquid inside of an enclosed container. And so in this example I've got drawn on the board here, where we've got liquid and then above it is a gas, this is the headspace. And there's also headspace in a 2-liter bottle of soda. You know, in the 2-liter bottle of soda, it tapers to the spout. Here's the cap. And usually they just put a little bit. And so in this area is the headspace. Henry's law, which is what we're going to be working with today, defines the ratio between a constituent in the headspace and in the liquid. So on the back page is Henry's law. It says C is P divided by K sub H. C is the concentration in the liquid phase. So in the case of soda, it's carbon dioxide dissolved. It's not that it's the bubbles in the soda, it's that carbon dioxide is actually turned into a liquid and it's mixed with the water inside of the soda. That's why when you open the soda, suddenly you see the bubbles are forming inside of the bottle. It's because the dissolved liquid carbon dioxide is turning into a gas. So C is the concentration in the liquid phase, and P is the pressure of the constituent in the gas phase. So you probably have noticed a difference when you hold on to a bottle of soda that's never been opened before. It's very rigid. But then as soon as you open it, even if you close it again, it becomes somewhat flexible. Has everybody noticed that before? The difference in like how firm the plastic feels? It's not that the plastic is changing. And even if you don't pour anything out, you don't pour any of the liquid, just as soon as you open it, and then if you close it again, it loses the pressurization. Because originally, when it's packaged, the headspace is at a higher pressure than the atmosphere that surrounds it. Okay, so this K value is a ratio that helps to define, if we rewrite it in terms of K sub H, specifically, then it's the ratio of the pressure to the concentration. Now in this example, I'm going to ask you to consider a 2-liter of soda similar to what we just saw, and first of all calculate the concentration in terms of moles per liter of the carbon dioxide in solution, and then see if you can think of how to calculate the mass of carbon dioxide used in each bottle of soda. Okay, so we're going to go on problem 4 now. How do you do that? You have to calculate the molecular weight for CO2. So carbon is 12, oxygen is 16, and there's 2 oxygens. No, because there's 2 liters total. It's asking what the mass is, not how much mass, not G per L, just the total G. Not the concentration. It's asking the total mass. Yeah. All right. If you look at the K value, you can see the K value here is liter atmospheres per mole. So that tells us our pressure units have to be in atmospheres. Well, originally you were given the pressure in the headspace in kPa, kilopascal. So one of our first steps is to convert from kilopascals into atmospheres. The next thing is just to use the Henry's law ratio directly, and we can calculate that the concentration, there is 1.39 moles of CO2 per liter of liquid. Now in part B, it's asking to go from the idea of moles per liter and take into account the mass. Carbon dioxide is 1 part carbon, which has a molecular weight of 12 grams per mole, and then 2 parts oxygen, and oxygen is 16 grams per mole. So if we add that together, 12 plus 32, that's 44 grams per mole. And in part B, it's asking to know the mass of CO2 that's used, and so we multiply the concentration by the volume. There's 2 liters of volume here in each bottle. We multiply it by the 1.39 grams moles per liter and 44 grams per mole. So it turns out to be 122 grams of CO2 for every bottle that's produced. And that's fairly accurate, you know, in terms of the actual amount of CO2 used in a bottle of soda. Okay, please be sure to leave your in-class exercise as you're leaving the classroom. And let's take one final look at the announcements here just to make sure that we know what's going on in the future. There is, all right. Homework 4 is due on Sunday. Then the class after that will have quiz 2. All right, I hope you have a good weekend, and I'll see you again on Sunday.